So the slides should be online. Actually, an earlier version of the slides are already online because this is an updated version of the MLSS 2018 presentation. But as we learned yesterday, it's always good to write things down. So if you want to take notes, please feel free to take notes. All right, so generative adversarial networks is a generic technique that has been developed a few years ago and has caught a wave of excitement in the machine learning community. So in this lecture, I will try to give you some of that excitement, some of that sense of excitement, but also try to give you an overarching framework by which you can interpret the many, many publications that come out in the GAN space. So what we are going to do today is part of this outline. So there will be 1.5 hours tomorrow and 1.5 hours now. And hopefully we somehow get somewhere in the middle, in between here and on this outline. So first we're going to have a very simple presentation on what probabilistic models are, much simpler than the presentations you have seen earlier. And then within that context, I will tell you how GAN models are actually different in the sense that they are implicit models and what challenges come with this class of models. We're also going to revisit the 1920s and learn a little bit about the principles of estimating models and what can go wrong, in particular the case of misspecification, so when your model is not accurately able to express the real data. And then finally, we are going to dive deep into the technicalities of GAN models. In particular, we are going to look at various types of divergences. And Arthur has yesterday already done a great job of introducing conceptually some types of divergences. And finally, the nitty-gritty details, how to get GAN models to work. There are some problems that you will experience when you try to work with GAN models, and I will tell you a little bit about the current understanding and the best-known practical techniques to overcome these problems. And finally, many of you are doing research in this space, in the larger space of machine learning. I will point out some open research problems that may be interesting to work on. All right. And by the way, interrupt me at any time and ask questions. So I appreciate the more interactive style. And if you have any questions, please ask them. All right, so probabilistic models. And this is my personal understanding. And I'm a simple person, so I have a very simple understanding. But I found that this explanation helps, especially when talking to engineers or talking to people who didn't receive a mathematical training. And my understanding is as follows. So let's think of an ordinary deep learning system or any kind of machine learning system that makes predictions. I like to think of this system as a box. And this box receives some input. And inside the box, there's some processing happening. And it's happening when I push this button at the top. Usually, for a deep learning system, this would mean that tens of gigaflops operations are happening on your GPU. And finally, this box outputs something. So we can look inside the box, or we can keep it at this abstract level. Now, a generative model is also a box, but there's no input. So what does that mean? So when I push the button, something is produced, right? Now we know that computers are deterministic systems, so they cannot produce interesting things that vary or that have some variety in the output. They would be forced to reproduce the same thing over and over. And so conceptually, what this box actually represents is a transformation of some random noise, some random number source, into some outputs. And so again, now we are back in the setting where we have a function that processes some input and creates some output, except that this input is not some observed measurement, but it's just a random number source. So why is this actually a useful conceptual understanding? This is precisely how the models that drive generative adversarial networks, how the models are represented. They transform a source of random numbers into some outputs. And this function is a deep neural network. So how do we create such box? How do we actually can learn this function in there? I mean, how to learn a function that transforms noise into interesting labels? And what is it useful for? I mean, how can I, now, even if I have such a box, what useful things can I do with it? Well, one extension of this would be to say, I'm not just constrained to, have a source of inputs that is random. I actually can consider the combination of the two approaches. I can have some input that is actual measurements and some noise source. And this is then very similar to what Bernard has shown in the sense of the structural equation models, right? We have a function that takes in some observations or some variables and random numbers and produces an output. And a particular realization. So the function is deterministic. There is no noise added at the end. The noise is an input to the function. So now we have three different types of boxes. Let's draw them. On the left, we have, I would say, classic, maybe non-probabilistic, although this is kind of not a fine distinction, non-probabilistic functions transforming some input to some output. And on the right, we would have what we call probabilistic models. And probabilistic models traditionally have been categorized into generative models and discriminative models. I actually don't know who came up with this distinction very first, but it dates back 2 decades or so. Where generative means that you only that you don't condition on any observations, and discriminative means you have also some observation in there. Recently, in the last 3 or 4 years, the terminology has slightly shifted. Initially, to my annoyance, now I have accepted that. After a conversation with Kevin Murphy, a chance conversation at iClear, we talked about this topic, and he was just using the term conditionally generative. And this is kind of, conditionally generative means discriminative. So you have both a random number source and you have an observation that you condition on. All right, so we are going to talk about this part in this presentation. Okay, probabilistic models represented in this form. Let's look at this function again. What is it useful for, right? What could we use this for? And how can we train it? So let me actually answer the second question first. So how to train this function? Fundamentally, the idea of GAN models has been a breakthrough in how to train these type of functions. And the idea here on a high level, we go into much more detail later, is that you use an auxiliary model to help you train this function. And the auxiliary model is called the adversary or the discriminator, but really it is just a binary classifier. And the way it works is as follows. You have your box with a button here, the generator. It's called the generator. And you have your training set, your data. And you want somehow to adjust the parameters of this function to match the statistics or match the outcomes of this training set. So the way you do it is you use this auxiliary model, and you hand this auxiliary model, which is a classifier, you hand it 1 out of 2 possible samples, either generated by the generator or generated from the training set. You just take a training sample. But you don't tell this classifier what it is. In fact, the classifier's job is to distinguish where did the data come from. Now, if the classifier is doing a really brilliant job and gets very high accuracies in distinguishing where the data is coming from, that is a certificate, that is a proof that you cannot have a good model, right? Because if it's easy to distinguish systematically the instances from the training set from the instances of the generated by the model, certainly they can't be equal. If it fails to classify accurately, so if it's like 50-50 chance performance, it's not a certificate of a good fit, because it could just be that the classifier is bad, right? The classifier could behave totally randomly. So, piecing this together, you simultaneously want to obtain a good classifier, and you want to fool the classifier by adjusting the parameters. And that's the basic idea. So the generator tries to fool the discriminator, tries to get a high classification loss, so high error rate, and that means generating realistic samples if this classifier is good. And the classifier tries to distinguish real from fake samples. So mathematically, this is fundamentally different from previous types of estimation problems in the sense that it's not minimizing some expected loss, but it is a saddle point problem. So you have the same loss function, the classification loss, but your generator model, or in this case a likelihood of the classifier, so the generator model tries to minimize the likelihood, which translates to a high error rate, and the classifier wants to have a high likelihood in terms of the classification decisions. So that's, for now, for the next half an hour or something, the understanding that we need. We will go into much more detail later. Any questions so far? This is a key slide. No? Good. All right, so now how can we use it, or what is it useful for? What's the actual applications? And this is where maybe the field of gun research is a bit underdeveloped, I would say. But that hasn't prevented people from actually working a lot on guns. And there's a nice statistic from Bruno Gavranovic, who collected statistics on the number of gun publications. So these are actually not gun publications, these are gun publications that have a unique name for their gun model. So, you know, A gun, B gun, C gun, D gun, you run out of letters, you have to do 2-letter combinations, 3-letter combinations. And there is 3, so this ends somewhere in or in mid-2018, there is 360 papers per month. This is the excitement that I mentioned. So, but what really are they useful for? And the application that we are all familiar with, that we have seen, is generating images, usually of beautiful celebrity people. But it's interesting to see just how much progress has been made. So there are experiments generating face images in the original 2014 paper by Ian Goodfellow and others from the University of Montreal, and they don't look very impressive. These are grayscale, blurry images. So you recognize a face there, but it doesn't have any real fidelity. And then you have the development, basically 1 or 2 year steps towards generating photorealistic, human indistinguishable, megapixel-sized face images. And that's really astonishing. And really the technology, the basic technology remains the same, and there's a lot more smaller variations and small regularization, different types of models, deeper models, the ability to train deeper models for guns, and all of these things compounding in generating these high-fidelity images. And if you have seen last month, NVIDIA released a new paper producing very, very cool visualizations of ImageNet images. It's still making progress, so it's not ending here. And so the next step would obviously be video, would be a more controllable representation by which you can say, I want not just a random person, I want a specific person or a person performing a certain, certain action or certain motion. And I see, there's still at least a few years of trajectory there. But that's really exciting. It's one application. And also, this has caused interest in, for example, game content creation, creating in the creative industry where you have to create a lot of variable content. This could be really a big step forward in making things more interesting. The situation with generating generic object classes, so not faces, is also making progress. So these are samples that were state-of-the-art roughly half a year ago. This is generic ImageNet samples, so they look kind of, what is that? Is that a dog or a sculpture or something? I don't know. But at least it's visibly making progress. If you go to object class specific generation, you get actually much more high fidelity generations. So single dog breed, a single type of bug, and so on. You get really quality. Actually, pizzas work really well because there's just texture. But even like abstract concepts, dog, shipyard dog, work. And so that's exciting. I think faces are very interesting as a research proxy in this domain because we humans are very much attuned to detecting faces. So there's this uncanny valley effect that if you synthesize faces and you don't get it exactly right, we immediately pick up on that. And so faces are good, but I think we have, as a community, done faces, and now we have to think about videos, about really rich visual content, and that will push the models a lot further. Okay, so that's some application. I think another big application of gun models is the generic topic of representation learning. And I agree that eventually everything will be causal representation learning, as we have heard. But what is representation learning, and how could it be useful? So representation learning, unsupervised representation learning in particular, is a stream that you can take a piece of data from a very complicated domain, high-dimensional time series, or an image or video or something, and you can extract from it a lower dimensional, more compact representation which contains factors of variation. And factors of variation are independent factors of variation which you can independently modify, and then you can recompose the original signal. And that would be interesting. I can show you one example here. So let's take a small image. So the image is high dimensional, even like a small image, you know, maybe 100 by 100 plus 3 color channels would be 30,000 dimensions. So in 30,000 dimensions, it's very hard to do, without strong assumptions, to do principled manipulation of the signal. So for example, the average of 2 images is not looking like a natural image. So even just linear manipulation of the signals don't work. But what we could do is, if we would have a powerful representation learning system, we could represent this image in a more compact way, say in 100 dimensions. And then we can ask this model to reconstruct this image, and maybe there is a loss, we lose some small details, but the essential structure is captured. And now we have a more compact representation, maybe with some imposed structure on it, that we can manipulate. So in this case, for example, I want to make this person smile. Right? I want to manipulate the representation, maybe animate the person, let them speak, things like that. And so for images, it's nice, we can visualize, we can play, the technology starts working actually. This is a real example. But wouldn't it be cool to have the same type of power for things like text? We heard the discussion about how to write well. Well, this would be really cool if I can put in a chunk, a page of text, the system extracting and separating content from style, from other factors, and then allowing me on a very powerful high level to manipulate or correct my writing. Or even like if multiple authors write, they have different writing styles, different writing ability. Wouldn't it be nice to kind of on that high level harmonize the style so we can all work on one big document, and the outcome would be as if written by a single proficient author. So that's kind of the dream of representation learning. And also representation learning would hopefully enable more data-efficient learning, because you could learn representations on one domain, and these representations, these more abstract, compact representations, would transfer and allow you to learn very efficiently on new domains. But if you think of technology in general, or machine learning systems in general, developing along the S-curve, so here we are kind of like at the early days, and here we are at the high level of maturity where it's broadly used. We are in representation learning, unsupervised representation learning, we are still in the very early days. And maybe there will be a fundamental pivot of the field so that we say, okay, everything needs to be causal, or maybe we'll just make progress in other ways, maybe using supervised representation learning. So for example, there are very powerful supervised representation learning methods, for example, word-to-vec, that are used widely across industry. So you don't have to go for unsupervised representation learning. But here's an example how GANs could be used for representation learning, and this example actually led to a huge interest in GAN models, which was the paper by Alec Redford in 2015. So he was able, using GANs, to generate these small bedroom images. I think these were 64 by 64 dimensional images, by training on, I think, 2.2 million bedroom images scraped from rental websites. And so the architecture was very simple. The architecture was what's sometimes called the DC GAN stack. So you basically start with a bunch of random numbers, in this case 100 random numbers, and then you have you reshape them. So you just say, okay, these are 100 numbers, now let me reshape them in a small array. And then you have what's called a transpose convolution, or sometimes called deconvolution layers, that iteratively halve the number of channels and double the dimensions. So 4 by 4 turns to 8 by 8, to 16 by 16, 32 by 2, and 64 by 64, and eventually you have 3 channels. So this is your final image. So it's just like a ConvNet running in reverse. And now the interesting thing is, so if I show you this as output of the model, there should be an immediate question, which is, this is a large neural network, did it not just remember all of these training images, right? I mean, they look really nice, okay, but did it not just remember these training images? And the exciting experiment that Alec Redford and his co-authors did to convince us otherwise was to show what happens when you take 2 points in this random space, so 2 randomly sampled points, and you interpolate along a linear line in this space, but you visualize the images. So if the network would have remembered all the training exemplars and nothing else, what we should see is that it jumps from training images to training images, and there would be no smooth transitions. Everything would be like a discrete transition, right? We would basically select images. But what actually happened is that a very continuous interpolation, where a window grows in size, the angle of the room changes, there's some curtains appearing, an object appears somewhere. I mean, this is my interpretation, right? The model doesn't have an interpretation of objects. But nevertheless, every one of these images along this linear trajectory looks quite realistic. And it's continuous and smooth. And so that caused tremendous amount of excitement, especially for representation learning, because it means that this network has somehow discovered a more compact manifold of the space of bedroom images. And another way they demonstrated the power of representation learning in GAN models was what has been demonstrated before on word-to-vec representations. And this, as far as I know, was the first presentation in terms of images. So what they did is they generated images, a few hundred of them, and manually labeled them as man or female, so male or female, and having glasses or not having glasses. So they just generated images and manually classified them. And then they took the median vector of a bunch of images. So man with glasses, they took the median vector in this latent space. This is the median image. They did the same for man without glasses and woman without glasses. And they just have now 3 latent vectors, which are the median vectors, and they did vector arithmetic in this 100-dimensional space. They get a new 100-dimensional vector, and now they can, using some variation, they can generate women with glasses. So there's nothing in the training data, there's no label in the training data. Why would the model organize a latent space in this way, where you have semantic directions which can be predictable, used to compose high-level concepts like glasses and gender? This was exciting. In terms of actually used deployments of GANs, I don't know very many. I have worked in industry for a while. I've talked to many other researchers. I'm not aware of deployed GAN models, maybe with one exception, which is the work by Twitter on performing super resolution of images. So this is not a generative model. This is a conditionally generative model. So it takes an observation as input plus noise. And the job here is to take a low resolution image and produce a high resolution upsampling of the image. So let's zoom in here. So on the left, you have this model is a ResNet. So this is how you would typically approach this with deep learning. You would write down, okay, I know how to do this. I make a deep neural network, and I make a mean squared error loss with a ResNet, like a really deep network, because you have essentially infinite training data. You can always generate training data by taking a high-res image and downsampling it. And on the right, we have the proposed super-resolution GAN model. And what you can see here is that the ResNet produces a good upsampling, but all the edges are blurred. That's a consequence of the mean squared error loss. It's a consequence of predicting point-wise, trying to predict a single point, a single decision point. The GAN model, however, produces very high fidelity, high-res images. And if you would draw a new noise vector, you would get a slightly different image, but it would still look realistic. So there was a huge improvement. However, you see that by measures in terms of the standard measure of image fidelity, you actually have a decrease, because these measures actually are very related to the mean squared error. So the architecture here is very much similar. It's a set of blocks of convolutions producing these. There's nothing super interesting in the architectures. All right, so these are just a small set of possible applications. GAN models have been used for other applications, but that said, they have not nearly reached the same relevance as, for example, recurrent neural networks have in real-world applications, or convolutional neural networks have. It's very early days. Any questions so far? Okay, so let's look more fundamentally before we actually look at different divergences and how to estimate implicit models. Let's look at principles of estimation. And for that, we have to go back to parametric models. So now we are in a generative case. And we're going to look at the simplest parametric model, just the univariate normal distribution. One of the simplest. So univariate normal distribution, you have a set of, in this case, density functions. Think of them as fine histograms. And you can modify two parameters. It has a mean parameter and a variance parameter. So if I modify these parameters, I get different realizations of this family of distributions. Right? So I have a two-dimensional index set, which is these mean and variance parameters, and if I move them around, I trace out the space of distributions. And the key property of these parametric models is that I have a density function, which I can compute. I make strong assumptions. So for example, the Gaussian, you make very strong assumptions about the tail behavior. It has very light tails, so it falls off very quickly. But you have more than a century of research in statistics and learning theory on how to deal with these type of models. So it's a super mature field. And the way you estimate these models, one very popular way, still very popular, actually the most popular way, is the principle of maximum likelihood estimation. So the likelihood is the object that you have already seen, the density function, but treated as a function of the parameters instead of as a function of the data. And maximum likelihood estimation is very popular. For example, if you do least squares estimation for regression, if you use softmax cross entropy in your deep learning framework, that's all maximum likelihood. And there will be a link to the divergences we will discuss later. If you do maximum likelihood estimation, you optimize the Kullback-Leibler divergence to the true distribution. So your model distribution, your true distribution, you optimize the so if your model is Q, if the true distribution is P, you optimize the KL divergence P to Q. So what's the likelihood function? Here's a graphical picture. We have a model, X given P, so X is our observation, X given theta. Theta is our parameter, so this would be mean and variance, for example. And we can modify these parameters and we would get these different distributions, right? So we can wiggle on theta or we can wiggle on X, but if we observe X, we have to somehow find a good theta. And one of these properties, if you look at these three different instances, one of the properties is that the integrated area is always 1, right? That's what the density function is. It integrates to 1. So here's the intuition for the likelihood, given that it integrates to 1. We have this density function and we throw in our data. So maybe four data observations. We have 4 points. And now we want to adjust the theta parameters to somehow fit these points. And the way we do it is we evaluate the density at these data observations. So we keep X fixed and we look at P of X1 given theta, and we do this for all of these 4 data items. So we fix theta to some value and then we can evaluate it. If we would move it, all these values would change, obviously. And the likelihood is a product of these lengths. So these sticks here, even in a high-dimensional case, it would always be lengths, right? The likelihood is a product of these lengths because we assume our data to be IID, independent and identically distributed. The likelihood factorizes. So the likelihood of theta is the product of the likelihood of the per data likelihoods. And so really, now we want to maximize this quantity. And that means we want to maximize the product of these sticks, right? The product of these lengths, product of these 4 numbers. So you can already see if there would be a data point here, that stick would be very small, the number would be very close to 0. If you take a product of many numbers and one of them is close to 0, the whole thing would be close to 0. So the likelihood really tries, is very conservative. It tries to give every one of the data items a certain length, right, of these sticks. Okay, so how we are going to do this? Well, we know all these lengths are positive, so the product of positive numbers is positive. And it's much more easy to work if we take the logarithm on both sides. So if something is positive, we can take the logarithm on both sides. It's a monotone transformation. And if we do this, we have changed nothing. We just added the log left and right side. But now we can apply, I think it's 8th grade or 9th grade logarithm rules, that the logarithm of a product is equal to the sum of the logarithms. Right? So we just swap these things around. The logarithm goes inside. And that's actually the log likelihood, that is what happens when you compute the softmax cross entropy. The cross entropy is just this expression, right? So when you maximize the sum of the log likelihoods per data item log likelihoods, you maximize the joint log likelihood. And then in mini-batch stochastic gradient descent, of course, you don't evaluate the whole sum, you do subsampling and so on, but that is kind of a detail. Okay, that's all we are going to do for the parametric models and the likelihood, but this is how most models are estimated, including recurrent neural networks, including convnets, including most deep learning models. Now for implicit models, for these models that transform noise into outputs, this does not work. And so here is here's an implicit model. We can see this as a function. Now I call it G. It was lowercase f before. I apologize. That transforms noise into an observation. And the problem here is, and these models are sometimes called likelihood-free models. The problem is that we don't have a computable likelihood function for two reasons. Either it exists and we cannot compute it tractably, or it doesn't even exist. However, we have seen that these models can be highly expressive. Right? Any distribution can be represented in this form. I can always transform a reference noise distribution, say uniform distribution, into whatever output distribution. There exists a function that does this. And they are so important because they form the basis of generative adversarial networks. But we have a comparative lack of theory and a comparative lack of learning algorithms compared to these more classic models. So if you look back, and Chuck here did a nice survey paper a few years back, together with Balaji, on implicit models. Actually, it slightly crops the slide. So there is a point here, reference number 1. So in 1984, the term implicit model was coined, and these type of models were considered, but they have not really been used very much. And basically then, the Goodfellow work sparked the renewed interest in this class of models. So what are the fundamental problems with this class of models? And that will lead to how we can overcome these. The first problem is, well, this function G may not be invertible. Right? It is a many-to-one map. It can map many noise vectors to the same output point. So if we think about the set of all possible noise vectors that we can have as input, if we sweep through that space, we sweep out an output space, a space of possible realizations. So if we consider this function here and we can consider how various points are mapped, there's nothing that guarantees that we don't map many inputs to the same output. So if we want to now compute the density in the output space, what we have to do is we have to consider the density in the input space and we have to solve the pre-image problem. We have to invert this map. So if there is a density, it would be the integral over the inverse set at an observation point x of this original measure. Right? So that would give us a way to compute the density. And however, it is very hard for deep neural network to do this inversion. And in fact, in deep neural networks, we do collapse dimensions. So we lose entire dimensions. So that's the first problem. Assuming a density exists, then we could do this. It's just very, very hard, so we can't really. The other problem is, I showed you the example from Alec Redford. It started with 100 random numbers, and it mapped that to 30,000 or 64 by 64 by 3. What is that? 12,000 output dimensions. We are in a setting where we start with a low-dimensional distribution here and map that into a high-dimensional space. And so the neural network cannot create new dimensions. So what happens actually is that we map it into a low-dimensional manifold. So the manifold that can be represented by the model afterwards is at most 100-dimensional in 12,000 dimensions. And that means if you have a new test image, for example here, almost surely you are off the manifold. Right? So there is no way your model can represent this image, any new image, because the chance that you're off the manifold is 1. And that's fundamentally a problem because it means that your model has 0 probability of creating this image. And with the likelihood, we have seen what happens if you have zero probability. If you want to extend the likelihood in this way, the likelihood would be zero. So your model would be infinitely bad. Your log likelihood is negative infinity. So more technically, the density is actually not defined on this output space. So that's why you cannot use, even in principle, likelihood-based training procedures on GAN models, the way we use it. What you would first have to do is you would have to fix the dimensionality of this input. And if you do that, you also would have to ensure that this function doesn't collapse. And if you do both of them, you have representations of invertible functions, and then you have functions which are very popular, which are called normalized flow models. So there is a class of models in machine learning, these flow models, which are invertible, but they're no longer GANs, and they don't usually produce so nice images. Okay, so that's two fundamental problems with GAN models. Let me talk about a third one, and this affects any machine learning model. Any questions so far on this? No? Let me talk about misspecification. So this is a concept which is often used in statistics. You say your model is well specified if there exists a parameter vector so that the model indexed by this parameter vector is the true distribution. Now, it's a bit of an artificial concept because we never have really access to the true distribution, and almost certainly in our model we make assumptions which simplify the situation, and we may not be able to even express the full model that we would like, and therefore in practice all models are misspecified. So misspecified is if this does not hold. So you can assume with certainty that your model, if you apply it to real data, is misspecified. However, then it's really important to think about possible consequences of misspecification. So what can go wrong? Because a lot of proofs, for example, the classic consistency proof of maximum likelihood estimation, relies on the assumption that your model is well specified, that there exists a parameter that indexes a true distribution. Okay, let's make a simple example. This example is reasonably famous, and it's about coins. Takes a second. Try again. Hope it doesn't hang. Okay. So this about coins. Yeah. Let me use a pound coin, or the 20 pence coin, I think it is. This example is due to Cosma Chalizzi and Bradford DeLong, and it's an illustration of what can go wrong if your model is misspecified. So I give you a coin, and I tell you the coin is biased. It's biased in one of two ways. Either the coin favors tails or it favors heads. You know, maybe I even tell you 80% it favors 80% heads or it favors 80% tails. But I don't tell you which of the two one it is. Right? So how would you find out? I give you the coin. You can actually throw it. You can do some experiments on these coins. Well, if you're Bayesian, I have given you lots of information about this situation. So what you would do is you would set up a hierarchical model. You would say, okay, I know it's one of these two possible situations. I have a likelihood, which is a binomial likelihood in this case, for observing a certain number of heads. So you would do, for example, 10 experiments or 20 experiments, and outcomes, 16 times out of 20 times it came up heads. So you want to use that information, and the way you use it, you have two models. So outcome A or outcome B, and you would have a closed likelihood. So it's a very accurately modeled setting here. And you would say that, okay, the posterior probability of this being A is just the likelihood times the prior divided by the marginal likelihood. So it's kind of the Bayes rule applied. But I don't know which one of the two settings it is, A or B. So I would have a prior probability of half-half. Right? So this is kind of like accurately capturing our full understanding. And it should be an efficient way to do inference. But now I trick you. I actually give you a fair coin. So you have encoded assumptions, but I've given you something that does not comply with your assumptions. So what would happen? You do your experiment. What would happen? So let's look at the posterior of the probability, the posterior probability of it being outcome A, so biased for tails, as you draw more and more coins. So I show you one realization here. So this is the probability of it being A given a set of k draws. So in this case, 60 draws. So things go seriously wrong, and you don't know they are going wrong. The first thing is, before you see any data, if you have to predict the next row of coins, you're doing a perfect job. Because you're uncertain about the two hypotheses. If you integrate over them, the next coin you predict 50-50 to be heads or tails. And that's perfect. That's the best you can do before you see any data. But now, your posterior beliefs concentrate. You're very, very certain, for example, here, that it is outcome A. 99.99% sure it's outcome A. However, you infinitely often revise your beliefs and are very certain it's outcome B. So it keeps jumping back and forth. And in fact, you can, using a single observation, you can almost entirely revise your posterior beliefs. So you're 99% sure it is outcome A, and then you see two more observations, and you're really sure it's outcome B. In fact, in expectation over the number of draws, the Kullback-Leibler divergence in the posterior predictive, so in this distribution, grows. So the more data you see, the worse you do. So that's a very pointed illustrative example of what can go wrong, even if you do full Bayesian inference, if your assumptions are wrong. Now here's another form of misspecification that affects GAN models. And this is what we called, in a paper, we called it dimensional misspecification. So we don't even get the dimensionality of our data right, which very few other machine learning models do. Most machine learning models actually work in the space where the observations live, and therefore they get the dimensionality right, because they have to put a density and have to put a likelihood. In GAN models, we most often are in the situation where we try to map a low-dimensional manifold in this high-dimensional setting. So this is another fundamental difference to most machine learning models. Okay, any questions on that? But in my heart, I'm a Bayesian, so this wasn't a rant against the Bayesian philosophy. I'm a Bayesian. But the assumptions really matter. So let's go to the next part. So we are going to look at divergences. And also, like Arthur has presented something on integral probability metrics. I want to build on that. And then later we will discuss generalizations, maybe not today. Before I do that, there is this huge set of GAN papers. And you've seen the statistics. There's tons and tons of GAN papers. And it at some point can appear overwhelming. You don't know the literature. There are many good ideas. Some have good images. Some have good equations. How to structure this. Sometimes it appears, and people have called this the GAN zoo. I mean, maybe you have been taking the time here to go on a safari. You can actually see these animals in this beautiful country. And as in any zoo, you have very beautiful species, pristine, nicely derived with principles. And like in some zoos, you have maybe not so nice species. So you have things that appear like a few hacks slammed together. And so my goal is not to give you a long list of what people have tried and what works and what is empirically good. I really try to give you a conceptual framework to understand current work and even future work, hopefully. So, and I don't have a chance to actually give you 350 different GAN models and explain how they are different. This just doesn't make sense. And the conceptual element that will structure all of this is these divergences. So let's speak about the space of divergences. We're going to map out together, we're going to map out the space of divergences. And as we map out the space, we will discuss different GAN models. So the model that you have seen already using this classification loss is sometimes also called the Jensen-Shannon GAN, the original GAN. And what we are going to do here is we enrich this class by, we embed this Jensen-Shannon GAN in a larger class called the F-GAN. And this will include the KL as well. So now we are on familiar territory. And there's another class, the IPMs, that Arthur has presented, and they intersect at this point here, the total variation. And in the IPMs, there's Wasserstein, there's MMD. And then there are new ones, the Fisher divergence, the Sobolev divergence. And they apply in different settings. So they apply in the dimensionally misspecified case, or they need further assumptions of densities, which will be this part, and that will give us new ways to generalize these divergences to the more general setting, to the misspecified case. So that will be our final picture. That will be our set of divergences, and so now we build up incrementally these set of divergences and discuss them in this order. Make sense? And there's no universal statement that says, one divergence is better than another. It's fundamentally like you choose your loss function. It is a subjective choice that depends on the problem and your understanding. And often we neither understand the divergences well enough or our problem well enough to make a good choice. So, all right. So let's start with the Jensen-Shannon gun. So this was this picture here with this classifier. And at the end, we have the saddle point problem with this loss. So where does this loss come from? Really how, it has an intuitive interpretation, like we said, it's a classification, log likelihood, right? The log likelihood of correct classifications, log likelihood of the incorrect classifications. But where does this come from? Can we derive this in a better setting? And can the idea of saddle point problems be generalized? And so the saddle point problems, the picture that we have right now in our minds looks like this, right? So we have, actually the animation, yeah, now it's playing. So we have this beautiful picture in our mind, a saddle point looks just like a horseback, right, in 2 dimensions. We can't think higher than 2 dimensions. So it's beautiful, and we basically can make some algorithms that converge to the saddle point, right? So this is kind of the picture that we have in our mind. Actually, the real saddle points don't look like this, and this will cause some real practical difficulties, and we're going to see this later. But for now, we can keep this clean picture in our mind. Let's talk about the Jensen-Shannon gun. In particular, the way we approach this is not to derive this particular Jensen-Shannon gun, but we directly derive the larger class. And these larger class are called F-guns, where F stands for the F divergence. And this was a NIPS paper of ours 2 years ago. So what is an F divergence? Arthur has already shown the definition. Let me show it again. The F divergence, first of all, makes strict assumptions. It makes the assumption that you have 2 density functions, P and Q. So the F divergence between 2 distributions, capital P and capital Q, is defined as an integral over some equation involving the densities. Not every distribution has a density. I showed you the example of mapping this low dimensional distribution to the high dimensional space. This doesn't have a density. And it involves an element f, a function f, which is sometimes called the generator function, which is convex. And it maps from the positive numbers to the real line. So really, it could be any function f that satisfies these criteria. Right, so that's the classic definition of the F divergence. Why are F divergences interesting? For one, they unify a large number of existing statistical divergences between distributions. So the Kullback-Leibler divergence is an F divergence. The reverse Kullback-Leibler is an F divergence. The Jensen-Shannon, the one that's used by gun models, turns out to be an F divergence, as we will see in a second. There's a class of alpha divergence. There are multiple divergences called alpha divergences, but all of them are F divergences. And really, very important divergences turn out to be F divergences. So if we can have a generic recipe for F divergences, that would be quite useful to cover all of these things. And I showed here on the right, these are all convex functions which for an argument of 1 evaluate to 0. Right? So you can see easily verify that if this is 1, it's 0, if this is 1, it's 0, 1, it's 0, and so on. So how many functions can you think of that are so simple that all satisfy these 2 things? If you find a new one, you can call it after your name. I mean, why not? So let's look at the F divergence. It's of this form. It's convex, and for an argument of 1, it's 0. We are going to work. We're going to derive together from the F divergence. We're going to derive the gun objective, and it will be a sequence of very simple steps. So actually, without writing anything down, you could do this at home afterwards. And the key object that we are going to use here is what's called the differential conjugate of a function. Sounds very sophisticated if you call things by German names. But essentially, it's a very simple idea. It means it's essential capturing the definition of convexity. It says any convex function has an equivalent representation, a variational representation. Let me first actually go to the picture. The picture will illustrate this simple idea. Any convex function f can be represented as a supremum, as a maximum over linear functions. So here's a convex function. Let's take any point on this function and create a linear lower bound, the tightest linear lower bound at this point, right? Which is just, if the function is differentiable, it's just a gradient, and then move it up. So if I do this not just as one point, but I do this at many points, maybe infinitely many points, I get back the exact function if I take the tightest possible bound over this family of linear functions. So I get a family of infinitely many linear functions, and if I fix a certain point and ask what's the tightest one, then I recover the value of the function. And this is exactly what this equation says. The function f, the original function, has a representation as a supremum, so taking the highest value over this family of functions, of linear functions. Linear because the argument u only appears here in the linear term. And then there is some f star function which actually correctly shifts up these functions, right? So f star depends on f. And this object f star is a constant. If I fix t, it's a constant, right? This is called the differential conjugate. So if we have f, we can derive the differential conjugate. So let's do that. Let's do that afterwards as an example. We will do the Kullback-Leibler divergence as an example, actually. Let's look at the original definition of the f divergence and just work with what we have learned right now, the differential conjugate. Let's work with that. So we have the original equation, and we plug in just this equivalence, right? We saw that f can be represented equivalently as the supremum over this infinite family of functions. This is the argument u, so we just plug in the argument u and f star of t, right? Supremum over t. So everything is the same, it's equivalent. Now, what we would really like to do is to swap the supremum and the integration. Right? So can we just pull out the supremum out of the integral? Oh, not in general. But here we can, and the way we can do it is, so at this point, when we evaluate, so let's look at this integral, right? If we evaluate the supremum, we have a fixed x value, right? We on this orange expression, we have a fixed value of x, and t depends on x, so it would be really t subscript x, right? So before we can pull out the supremum, we would have to somehow do something about the t, because we would lose the dependence of t on x. And the way we do it is we go from a lowercase t, which is a scalar that we optimize, to a function, t of x. So t of x is now a function, and that allows us to actually pull out the supremum. And if we pull out the supremum, we have this capital T of x here, pull out the supremum, we can apply just this basic distributive law of taking a product with a term, and that cancels the q term, so this q term goes away, and it adds the q term to the second expression, right? So it cancels here, and then we actually add it here. And now the interesting thing about the resulting object is, these are two integrals over distributions, p and q, and integrals over distributions are also, you can write them equivalently as expectations. And this is very similar to the Gunn objective. So what we have written is that the f divergence can be lower bounded because this function does not allow every possible dependence on x, but it's constrained to be a certain set of functions, like a neural network. We have introduced this extra function, the discriminator. T of x is a discriminator. And as a result, we have lower bounded this f divergence variationally. So if we modify t, we get different set of lower bounds. And the interesting thing about expectations is also that you can approximate them with samples. Instead of taking the exact integral, which you can't because it involves a distribution you don't know, you can now approximate these integrals using samples. So that's a derivation. Maybe you can do it at home, I don't know. But the conceptual idea is quite simple. And let me be clear here, this was done in 2010 by Xuan Longguyen, Martin Wainwright, and Michael Jordan. And we just made the connection of their work to Ian Goodfellow's work. So just to be clear. We also derived all these variation representations for all the F divergences in the table, so you don't have to if you don't want to. Now, if you compare this F-gun formula with a gun formula, the lower bound here, so supremum becomes a maximum, right? So the maximum, the inner part is this representation, is exactly what we had. But then you want to optimize, you want to minimize this divergence. It's like a distance, you want to minimize it to have a good generator. So now a minimization is added in front of this. And so if you compare the original Jensen-Shannon gun from Ian Goodfellow with the F gun, we see it has very much the same structure. And in fact, there's an exact equivalence if we choose this function t of a certain type. And that shows, as already pointed out in the original Goodfellow paper, that the gun minimizes the Jensen-Shannon divergence. So let's do one example together to put this in practice, and then you will see how simple it is. And we are going to do the Kullback-Leibler divergence. So the Kullback-Leibler divergence, the most popular divergence in machine learning, I would say, is defined as p log pq, right? So you have two distributions with densities. You take the expectation over p of the density ratio through the logarithm. So the logarithm is concave, right? So first we have to do something about that. It's not an F divergence as I've written it down, but we can easily fix that by just taking the negative logarithm. Because the negative logarithm is just negative logarithm of x is just the logarithm of the inverse of x. So now it's convex. And indeed, if the argument is 1, so if qp is 1, then the logarithm maps it to 0. So we are now in the F divergence regime. The first thing that we need to do is we somehow need to find this Fenchel conjugate object, F star. Right? We have to know this object in order to write down these gun-like saddle point problems. So let's write that down. It will turn out we just plug in the definition. So we have the F object, the green one, plug that into the, instantiate the F here, right? And then we get this expression. So we somehow need to solve this for any t. And that's very easy. It's a scalar problem. So we just start here. We can just set the gradient of the inner expression to 0. So we just find the maximizer. And that gives us that u is equal to minus 1 over t. Right, so this is just basic math. And then we plug that definition in. So f star of t is a supremum over that. We know where the supremum is, so we plug in the u. That maximizes it. So minus 1 over t, we plug it in here, we plug it in here. That gives us minus 1 minus log minus t. And that already tells us this does not work for all t. Right? So if we would put in t equals 5, the logarithm of minus 5, if we want to stay in the real numbers, is not defined. So we have to constrain the arguments of t, and that is called the domain of f star. And it is important, but we did these derivations for you. So we just know that t has to be smaller than 0. And now we have the f star object. And given that we have the f star object, here it is, we can just plug it into this generic formula, and we get the equivalent gun-like objective for the Kullback-Leibler divergence. So this wasn't very hard, right? Some divergences are harder than others. Actually, I did this table for the NIPS paper, and like there's 8 or so different divergences, and 3 of them I got wrong in the initial derivation. And then I checked with a colleague of mine, with Botond, and now we are pretty sure that all of them are correctly derived. So here is a conjugate object and the domain that you have to respect. And you can just plug it in and get all of these divergences. Any questions so far? Yes. Right, so you mean the last column? The last column is relevant insofar as it allows us, if we assume our discriminator can represent any function, then we get an optimal form that involves the derivative. And actually not the derivative of 1, but the derivative. So this is a constant offset that makes the divergence 0. So that's the relevance of this column. But the derivative also has another purpose. The derivative of f also allows you to directly write down what the optimal discriminator function looks like. So if you would know the density p and you know the density q, what does t of x look like? Right, the value. Is it 4.1? Is it -3? Right, and using the derivative of f, you can directly write that down. Okay, one more property of f divergences before we kind of zoom out again. They always come in pairs. So if you have an f divergence, you can always get another f divergence, which swaps the two arguments. So it's just good to know. And the function g has a very simple expression. So that's just good to know. All right, so now this is a setting that we have. We have charted out some of this territory. We have the original Jensen-Shannon, we did the KL together, and we know that the space of f divergences is now accessible to us. Let's actually look at a code example. The links are in the presentation materials. But I want to show you maybe two examples. Sorry. So, can you see? No, you can't see it. 1 second. Okay. Yes. So this is a simple toy example, generating. So it's online at GitHub. You can find it using PyTorch. We generate some training data from a univariate normal distribution, actually from a t distribution. And we want to fit that using a univariate gun model. And this turns out to be surprisingly difficult. So this already tells you that using gun models for accurate density estimation is very tricky. So this is the real underlying true density, and this is a sample, 10,000 samples, I believe. So now we set up a gun model using the generic F-gun formulation. And we start, so we import a few torch things, and then we start with this abstract object, right? So this is really very close to the paper, to this table. We implement this conjugate dual function, so this F star function, and we just say, okay, if it's KL, then return this. If it's KL reverse, return this, and so on. So it's just this table, implementing this table. And F star t is a composition of F star and this discriminator function t, and again, it's just taking this argument and mapping it through this very simple functions that you have seen in the table. Okay, so this is really, I just want to show you this object that is very close to the table. There's no difference in implementation. Now, let's look at the simple part here, the generator and the discriminator. The generator maps noise to the real line, right? And the way we do it is we take one noise variable, we map it to a certain set of hidden variables to get certain richness, and then we collapse it again to one variable. So very simple. One relu, 2 layers. The discriminator is just a 2-layer MLP, mapping to the real numbers. So this is really as simple as it gets. And now the interesting thing is the F-gun learning objective. So if you're familiar with PyTorch, it is very close to the picture of generating random, generate random variations, and we have the real data, x real, right? So we map x real to the statistics, t real, of the discriminator, and we now generate, we have z model is noise, we map that to samples from the model, and we do the same mapping that we did to the real data, except now we apply the f star. So this other part, the second expectation had the f star, the first part didn't. And then we have the losses, generator and discriminator losses, which are actually the same because the generator does not depend. The way we split it, the reason why we split it up into two loss functions is that we need to take steps in the different directions, right? So it's a saddle point problem. So from the generator perspective, you want to optimize in one direction, and from the discriminator perspective, you want to optimize in a different direction. So that's why these two different loss functions appear. And then there's some important thing without which it wouldn't work, which I talk about later, which is how to regularize a discriminator. And so we use a concept here called gradient penalties, and we get into that later. And then really the optimization is instantiate a generator, instantiate a discriminator, compose them in this learning objective, and then we optimize, in this case using Adam, we optimize just by drawing the data. And the losses go up and down. We don't know. It's not a minimization problem, it's a saddle point problem. So you don't know whether you converge or not, because it may just very, very much fluctuate. And you don't know what the target value is. If you do softmax cross entropy for classification problems, you know that going close to 0 is a good thing. Here you don't know. And finally, we can draw samples from the model. So what you see here is a very poor fit to the density. But at least it has got basic things like the moments right. So doing density estimation with GAN models is not easy. Good. That was a depressing example. Let's pick a more exciting example. Let's do images. And this will be on little images, CIFAR. So I can run this actually efficiently. And actually, let me show you first the results. So CIFAR images are small. I made them even smaller here for you, so you can basically see there are some colorful things happening there. But they don't look so bad. So let's go back to this example. It's exactly the same conjugate dual function. So nothing has changed here. Nothing has changed except in the generator and in the discriminator. The generator now is a DC GAN stack. So exactly the stack from Alec Radford. So a couple of transposed convolution. And also here, adding batch normalization really helps, which is a bit disappointing, right? You know, that you have to add batch normalization. But basically, you map noise through a number of stacks, and in the end, you get an image, directly an image out. And the discriminator is just a convnet. Discriminator is just a convnet with a binary classification. The FGAN learning objective stays exactly the same. Now we have to train on the GPU. And we optimize. And one thing I want to show you is look at the objective. This is all over the place. Objective goes up, goes down, goes up, goes down. Eventually it becomes a constant. We don't know whether the learning takes place. This is one of the dissatisfying states of doing experiments with GANs. You don't know, you don't have a clear statistic which you can observe whether you make progress in the learning. Okay, so all the code examples are online. Of course, if you want to do GANs on images, I don't encourage you to start there. I encourage you to go to GitHub and search whoever has the best model at the moment, but this is a didactic example that's very close to these equations. Okay, if you apply the same model to higher dimensional images, so there's a thing called Tiny ImageNet, which is the next level up from CIFAR 10, you get some image-like things, but something very dissatisfying. So even from the distance, you can see that these are not real images. So to go to the images I showed you before, you have to use very deep networks, for example, ResNets, to get the high image fidelity. So the architecture choice matters much more than the divergence choice. Okay, so that's that. Any questions so far? Yes? Yes. So, I mean, there's clean mathematical conditions for Neumann's kind of type theorems when you are allowed to exchange min and max. The way we have it now is actually the way we derived it, right? We have a divergence, which is lower bounded. So you want to get that lower bound as tight as possible to get an accurate estimate of the divergence. But then we want to push down this lower bound, right? We want to have a good model fit. So swapping it around, I'm not sure is that we can do it. I would have to think about it. I don't think anyone has tried swapping the min and the max. Now, guarantees. I think this is a very important question. So the question can be posed on multiple levels. The question can be posed on the statistical level. So what can we say, independent of the algorithm that we choose, independent of the optimization dynamics, about existence of saddle points and what saddle points, if they are multiple, are preferred, right? Or if they're, for example, as we get more and more data, does the number of saddle points decrease so that eventually we only have one saddle point? Are they all equally good? Things like that. So we can ask that. As far as I know, this hasn't been addressed. Right? So we have good results, good established theory for things like maximum likelihood for the likelihood function. So we know that the concentration around the maximum likelihood estimation, maximum likelihood estimator, what happens there. We know the rate of the concentration. We know what happens if the model is not in a true, if the true model is not in a set of representable models. So in a misspecified case, we know what happens, how it concentrates. So we have well-developed theory there. All this theory is missing for GANs. So that's one problem. You can ask the problem also more practically, right? So if you know that there's a saddle point and you're willing to make some assumptions about the saddle points, do we actually have algorithms that can find these saddle points? And I will get to that actually in half an hour or so tomorrow. So let me see if there's anything else. So I think this is something that needs to be addressed, but I don't think we are currently at this stage yet. I mean, I would like to see such studies or such theory actually that starts from a statistical point. Yeah, the structure of the saddle points is degenerate in many ways. So we have actually the clean assumptions that I showed you. This prototypical saddle point is, it's strictly convex in one set of dimensions and strictly concave in the other set of dimensions. It doesn't happen. So, so one way how regularization has been developed for GANs is to actually ensure that certain properties that are a consequence of these nice structures, for example, guaranteed convergence, that they still hold. So you can prove this in low-dimensional settings. But the generic theory, I think, is nowhere near where it should be. And there are people smarter than me that should look at this. Okay, let's talk about integral probability metrics. Or are there any other questions? Yes? Yes, there are conditions under which that bound is tied. Actually, in our NIPS paper, we show what the optimal discriminator function is. So you can, if you have the density ratios, it's a very simple consequence of taking the derivative of this f function. You can write down in closed form the t of x star, so the t star of x, the optimal discriminator function, and that gives you the exact f divergence. Right? So now the question is, okay, first of all, we cannot compute it, but let's say we could compute it, right, in synthetic examples. Can we represent these type of functions easily with a neural network? So there are conditions, but they are very simplified. So this is kind of like, it's almost the most luxurious assumption you can make. Your function class is rich enough to contain the true thing. The bound comes from two things. The first thing is, actually from three things. The first thing is your function class may not be rich enough. So that's kind of the, it's called the approximation error. Then there is an estimation error, so you have finite samples, you don't have infinitely many samples. And then additionally, because you actually optimize the parameters, you have an optimization error. So the addition of these three errors lead to the gap between the true F divergence and the actual F divergence estimate that you output. Okay. Integral probability metrics. So we already saw Arthur speak about this. There's a nice review paper by Bharat Sripridumbadura who did a JMLR article on IPMs, and there's a huge table of IPMs in there, very much like the table I had on F divergences. And not all of these IPMs have been used in deep learning yet. So if you're looking for new divergences to try, this is a great source. So what is an IPM? An IPM is I think conceptually much simpler concept than F divergences. It says okay, I have two distributions, P and Q, and I'm searching for averages over P and averages over Q of some function f. And so I want to find a function f that is high on one distribution and low on the other distribution. So on realizations of one distribution, it should give high values, and on realizations of the other distribution, it should give low values. And if I can find this for the distributions, obviously these distributions can't be the same. If I search over very many functions and I'm unable to find a function, then surely they are likely the same. So it's a very intuitive concept. Let me actually show you a figure. So here we have realizations from two distributions, the green distribution and the orange distribution. And so I want to find a function that pushes the green points up, actually down in my visualization, down, and the orange points up. So let's find such a function. The problem is, if I allow any possible function, obviously I can send the orange points to infinity and the green points to negative infinity. Right? So if I allow every possible function, so I can't do that. I have to constrain the functions that I search over in some meaningful way. So let's constrain them to functions which at most increase with a slope of 1 or decrease with a slope of 1. Right? So functions of bounded variation, or Lipschitz bounded functions. So here's an example. I take the orange function and I push up the orange points, and I try to push down the green points. And here, this green point, it's not really possible to push it really very much down because I'm constrained, right? I can't go at a slope steeper than -1, right? But now I have constructed a function, this orange object f, in this class of functions that I search over, that satisfies that I have high values on the orange and small values on the green. So that's the basic idea. Obviously, the thing on the right is expectations over distributions, so infinitely many samples. And here I showed you an example with just a few points from this distribution. So there is an error that I make by putting in my finite sample here, my small training set. And now the IPMs are all of this form, they are all of this structure, and the only way they differ is by this choice of functions. Right, by the class of functions that I search over. So I showed you the Lipschitz bounded functions. If I use f as a reproducing kernel Hilbert space, like Arthur likes to do, then I get a different result, a different IPM. All right, so here's another class. For example, which one is this? Bounded functions, so the total variation function. If I choose bounded functions, so between -1 and 1, then I get the total variation divergence, which is also an F divergence. But this is very hard to work with with a finite sample case because I can make these line segments as small as I want. Right? I can't send them to infinity, but if I don't have two realizations exactly at the same point, which has probability 0, then I can't do this. So total variation divergence is tricky to work with, as Asa has already mentioned. All right, so we had this map here. So now we have the set of IPMs. Let's pick a single IPM in there and work on this. And then probably we have to wrap up at 10. Yes? Yeah? Okay. So let's do the maximum mean discrepancy and then we wrap up. So the maximum mean discrepancy is one type of IPM where the set of functions is from a space of functions called the reproducing kernel Hilbert space. It sounds so long and scary, but really it has some very nice interpretations. And I can go a bit high level on this because Arthur has done a brilliant job at explaining this. The beauty of using the MMD IPM is that you don't need to solve this variational problem. This variational problem has a nice closed form solution if you use the MMD, the reproducing kernel Hilbert space. And that's kind of the key advantage of this. The way, so there is a theorem that says, actually in Barrett's paper, in Arthur's paper, that this corresponds, and if you solve this problem exactly, corresponds to a norm in the Hilbert space of the kernel mean embeddings. And these kernel mean embeddings are this new object that you do, that you define. as a benefit of this, so the structure is as follows, right? You define this MMD over this class of functions. Smart people do some theorems that show it has a closed form solution. And then you approximate the closed form solution using your finite sample. And so this is called an estimation. So we estimate the MMD. It's not the true MMD, we estimate it. And there is an unbiased estimator that can allow us to estimate these MMD squared, actually. And the estimator then has a very simple form that we can actually simply compute. We compute a kernel matrix between our one data points from one distribution and take an average of the kernel values. We do this for the other distribution, and then we subtract twice the cross-kernel values, the average of the cross-kernel values. So implementation-wise, if you don't want to go into all the theory, implementation-wise it's super simple. You compute one big kernel matrix, and then exactly as Asa has shown, you chop out these three parts, the distribution 1 kernel values, the distribution 2 kernel values, and the cross values, and you compute the simple expressions. And that gives you an estimate of the MMD squared. Now, precisely this objective function has been used also for deep learning. Actually, there's 2 papers in parallel from Toronto, so Ujia Lee and others in 2015, and also Carolina Tsugate and also Zubin and others, and Dan Roy have done this at the same time in ICML 2015. They have used this MMD training objective, precisely this training objective, to train a deep generative model. And I think it's very nice to see that kernel methods are useful for defining training objectives on deep learning models. And we had a paper in NIPS 2016 where we have, from a completely different angle that I will show you in a second, came to the same objective function. And recently there's also, they have been used for exposing deficiencies of deep generative model. So Asa had an example on that where the slant of the one digit in MNIST was exposed by these tests. And there's some ongoing work on how to get more discriminative kernels, how to make these models work. The problem is, with MMD, the images don't look that nice. So this is from the original work of Carolina. Doesn't even get the MNIST. And you know, everybody can get MNIST. So that's kind of like the dissatisfying thing. It's so beautiful, it makes lots of sense, and yet quantitatively it doesn't give you the nice results. But you know, you don't have a lot of problems. I mean, you implement this, it works the first time. So if you have low-dimensional data, or if you have very good kernels, you can probably use this quite effectively. So I want to just give you, in the last 5 minutes, I want to give you another interpretation of the MMD, which we only found out later, this connection, because we came at it from a different angle. And this is a paper we had at NIPS 2 years ago, 3 years ago should be, 2 years ago, 2 years ago, called Disconets. Not the best name. But we said, okay, how to represent a function f, where actually we want to have a conditional probability. So p of y given x. We want to represent p of y given x without restrictive assumptions. So what we do is we use an implicit model. And the way we do it is we have so standard implicit model, we feed in noise, and we produce an output. Actually here, we feed in x and we produce an output. So normally what you do is this. You do empirical risk minimization. Right? This is the bread and butter of machine learning. You write down a loss, you predict something, f of x, and then you compare it with the ground truth that you have. And for example, you use the squared error or the absolute error, and then you minimize the error in expectation. So you do an empirical expectation of this thing. Empirical risk minimization, decades of experience. So what we do now is we append noise to the input. Right? So instead of just an expectation over the data, we also have an expectation over the noise, and we add the noise. But this is not very helpful. If you ever have completely noise inputs to your neural network, the best the neural network can do is to completely set all the weights to 0 that correspond to the noise dimensions, right? Because they literally contain no information, and the loss says, give me your best single guess. And the best single guess, obviously, is 1 point. There is no variation that's encouraged, right? So this does not work. We can't infuse somehow, you know, a distribution by adding noise to the input. But instead, what we do is we add another term, and this term says, whatever you predict, you take the loss of two separate predictions and you add the negative of that. And so this has a very simple interpretation. You minimize the expected loss minus some diversity term. So you should predict to have low loss, but keep things diverse as measured by the loss. So that's intuitively, everybody can understand this. Keep things spread out, but do well on average, right? Now, we can choose arbitrary loss functions. And there's so basically the work that we arrived at this objective function dates back to a paper from Rao in 1982, who already proposed this type of statistical functionals. And there's a particular choice of weighting these two terms, which is 1/2. So it struck us that there is a nice connection, and one connection is if you choose particular losses, then you actually have kernel functions, so conditionally positive, definite kernel functions, and then this corresponds exactly to the kernel MMD objective. So this is not a crazy idea. This actually precisely maps to kernel MMD if for particular choices of loss functions. And also there's another theory from Tilman Gniting and Adrian Rafteri related to proper scoring rules, which are statistical functionals which allow you to fit distributions. And there's also a link there. So it's not entirely crazy, and actually it worked for us. So what we did with it was to do hand pose estimation in 3D. So the input is here input depth image of a hand obtained by a time-of-flight sensing device, so like a Kinect, for example, Kinect 2. And so we do a ConvNet, we process this image, and we could ask it to produce a single best guess of the pose. But some poses are very uncertain. So if I show you my hand like this, you don't know what my fingers are doing, right? If I show you my hand like this, you have a lot more information and you can make an accurate estimate. So the uncertainty depends on the actual observation. So a simple additive uncertainty model like a Gaussian or something would not do justice. So what we instead do is we concatenate, inside this ConvNet, we concatenate a noise vector. And depending on which noise we actually do, we get different poses. And then we use this objective function to get the P of y given x, where y is the hand pose and x is the observed image, by optimizing this function. And so that works really well. So you get, like, for clean poses, you get low uncertainty. For bad observations, you get high uncertainty. And it's relatively low dimensional. So I think this is around 60 dimensions. Okay, I think we stop there. We're perfectly on time. And then maybe as a teaser, we now have charted out the MMDs. And tomorrow, I think Marco will talk about it today, but tomorrow I will also talk about Wassersteingans. So, and we will build sandcastles. Okay, thank you.